So in this lecture we proved three versions of Nullstellensatz. So the first version is this. So we start with K a field and A be a finitely generated as K algebra, but A is also a field. So first thing, it is finitely generated as K algebra. Second thing, it is also a field. So then A is algebraic over K, and this dimension of A over K is finite. So that is, it is a finite field extension. Now if this base field is algebraically closed, this K is algebraically closed, then we will have A is equal to K. So let us prove this, and for the proof of this we will use Noetherian normalization. So the normalization tells us there exists Z1 to Zm in A which are algebraically independent, and A is finite over this ring R, which is K Z1 to Zm. Now we have an integral extension from R to A. So this is what was our entire thing. So A is finite over this, and in fact we show that A is actually an integral extension of R. But what we are given is, now we come to the, so this is all till now is our Noetherian normalization. A is a field. Now if A is a field, if and only if R is a field, because A is an integral extension of R. So this also we have proven before, again in the lecture on transitivity of integral elements. So this was used in this proposition. So let B be an integral domain and A a subring of B such that B is integral over A. In order that B be a field, it is necessary and sufficient that A be a field. So B is a field if and only if A is a field and A is contained within a B. So similarly here R is contained within A. So A is a field if and only if R is a field. But R can be a field. So R is of this form, K is Z1 all the way to Zm. So R can be a field only if this M is 0. You cannot have a field when you have these polynomial ring kind of a thing. So you don't want all these variables. So M has to be 0. So this can only happen if M is 0. So thus A is finite over K only. So A is just finite over K. So you have this. Now if K is algebraically closed, then we do not have these field extensions like this. You just don't have any field extensions. So the only case left now is K is equal to A. So that was our first version of Nullstellensatz. So our second version of Nullstellensatz is this. So let K be an algebraically closed field. So we are going to use this thing here, that A is equal to K. So because our base field K is algebraically closed. So K be an algebraically closed field, then we have to prove that the maximal ideals in this ring K x1 to xn are of the form x1 minus a1, x2 minus a2, xn minus an, where this A which I'm writing here is just this tuple of points a1 to an in this space, affine space akn. So let us prove this. So let this M be the maximal ideal in this polynomial ring. So if this is a maximal ideal, you can modulo this polynomial ring with this maximal ideal to get a field. And this is a finitely generated K algebra. So here we are saying that if A is finitely generated as a K algebra with A a field, and then K is algebraically closed, then A is equal to K. So precisely by this version 1 of Nullstellensatz, we have A is equal to K. So this is what we are saying is our A. So this K we are saying is isomorphic to this A. So there is one-to-one correspondence. So this x1 you can modulo out with this maximal ideal to get x1 bar, x2 you can modulo out with maximal ideal to get x2 bar, xn you can modulo out with maximal ideal to get xn bar. So you have this correspondence. You have xi bar here, and it has to have some correspondence with some element ai here. So that's how you will have isomorphism. Or this ai will get mapped here to some ai bar, say in modulo out with m, or you can say that this implies that x1 minus a1 all the way to xn minus an lies in m, precisely because of the correspondence. You modulo out with m uh, you will get x1 bar here, but then this a1 comes from this string here, because there has to be some correspondence of this x1 bar with some element here. So this lies in the maximal ideal. But ideals like this are always maximal. x1 minus a1 all the way to xn minus an. This ideal is always maximal. And this is the ideal which we are denoting by m sub a. So since this is a maximal ideal, it is contained within m, there has to be an equality here. So this is so what we have done here means that the points, see these points a, corresponding to every point a like this, you have a maximal ideal like this. So there is one-to-one correspondence with maximal ideals. So for every point a, you have a corresponding maximal ideal. So this is the one-to-one correspondence. So now we do the version 3 of Nullstellensatz. So say we are given an ideal of a ring A. This ring A is finitely generated over a field K. So then the radical of I is just intersection of all maximal ideals which contain this ideal I. So M is a maximal ideal lying in A. So notice that for an ideal in any ring R, or say some ring B, we have the radical of I is just intersection of all prime ideals, where all these prime ideals contain this ideal I. So here we are saying is maximal ideals. So first thing you notice is that maximal ideals are prime. So this containment follows from maximal being prime. So this radical of I is always contained in intersection of prime ideals. But this is a bigger set of P of prime ideals. All these maximal ideals are prime, but there are more prime ideals than maximal ideals. So this intersection is going to be smaller. So this thing is going to be contained within this. So we have this containment. For the opposite containment, what we start is we start with the F which lies within A, and F does not lie in radical of I. So then we will show that F does not lie in the intersection, and to show that F does not lie in the intersection, we have to find a maximal ideal M such that F does not lie in the maximal ideal M. So let us start this. So F does not lie in the radical of I. So F does not lie in a multiplicatively closed set S, which is this just 1 F, F square, F cube, contains all the powers of F. So this implies this ideal intersection with S is just the null set. So now we are going to use some facts from before. So if you have something like this, then we can always construct a prime ideal P such that P contains this ideal I, and P also does not intersect the multiplicatively closed set S. So this is our fact 1. Fact 2 is we can localize our ring A at S, and we can get this ring S inverse of A, and it will have this maximal ideal S inverse P. So now only thing left to show is that P is maximal. So we have such a relationship. K goes to A modulo P. This is some integral domain. So A is finitely generated over field K. So you always have this relationship. This injects into this field S inverse over A over S inverse over P. So this is maximal. So we can set this thing as R, which is a field now. So A over P is an integral domain precisely because P is a prime ideal, and therefore it will inject into this field R. Now by 1 we will have that R over K is a finite field extension. So R over K would be a finite field extension. So this will make R integral over K, because if you have a finite field extension, then you are integral over that element, because you can always find monic polynomial corresponding to the finite field extension. Take any element, you have a monic polynomial corresponding to that, and that will give you the integral relation. But this A over P lies in our field R, so this is integral as well. So but R is a field. So if R is a field, then we have seen before A over P also has to be a field. So this would imply R is a field, that implies A over P has to be a field. So A over P is a field, and this implies that P is maximal.